So on the paper I have drawn, crudely as it turns out, but the best I can do, an oscillating system. An example of oscillatory motion. So here's the situation. I have a spring constant K, and I've attached to it a mass M, and I've put this on a frictionless surface. So there's no mechanism for energy to leave this system. We have a conservative system now. I'm idealizing the spring. I'm not going to lose any energy there, and there's no friction. So I start out by compressing the block some distance delta x. Now let's just call this negative a. I'm assuming to the left is negative and to the right is positive. That doesn't really matter which one you start with. Let's start with this. Delta x is equal to negative a. Remember, this delta x is going to be measured from the equilibrium point of the spring, the unstretched length. That's the unstretched point, I should say. That's how we handle springs. And I'm at rest, so my velocity is 0, or my speed is 0, I should say. And then I'm going to let it go. Now what's this thing going to do? Well, you know how springs work. The force is going to push the block this way. It's going to accelerate. There's an imbalanced force on it, so it will definitely accelerate. The speed will start to increase because the acceleration is in the same direction as the motion. And eventually it's going to come here. Now what I've tried to draw the spring at its unstretched, uncompressed length. So this is the equilibrium position of the block. That's represented here by delta x is equal to 0. There's no displacement from equilibrium. Now what has happened to the block at this point? It's sped up and sped up and sped up. The acceleration changes, of course, because the force is not a constant. Remember what the spring force looks like. F is equal to minus kx. Force is not constant, so the acceleration is not constant. But the block, there is still an acceleration, so the block still speeds up to this point where I've reached maximum velocity. How do I know it's maximum velocity? Because I know what's going to happen after it passes through this point. I then start to stretch the spring, and I get a buildup of a force. I get an increasing force, but in the opposite direction. Right over here, the force is acting to the left. So the acceleration is now going to be opposite of the motion, and it will start to slow down. And so it speeds up as it gets to this point, and then as it passes through, it starts to slow down because the force is accelerating it in the other direction. So at some point, I'm going to get over here to the speed of 0. And my displacement now, if my spring is idealized and there's no friction, all that good stuff, the conservation of energy says that the displacement from an equilibrium position now has to be just a, as it was negative a over here. If it's more than a, then somebody added energy. If it's less than a, then somebody took energy away. But I haven't given any mechanisms for those to occur. So I reach the same displacement from equilibrium over here. Okay, we can call A, and I picked the letter A on purpose. We can call A the amplitude of the motion. In essence, A is the maximum displacement from equilibrium. Now it's negative A over here and A over here. When you talk about the amplitude of the motion, we typically just pick out the positive value and don't worry about the negative value. And we just understand that that number we say could be positive or negative depending on what the block is doing at that time. But we call A the amplitude of the motion. All right, our goal here is to characterize this with some sort of mathematical function, okay? And I alluded in the earlier video to the fact that we know a couple of cyclical mathematical functions which seem like prime candidates for describing this motion. And, excuse me, those candidates are the cosine function and the sine function. Which one am I going to use? Well, if you've studied some trigonometry, or at least some pre-calculus, you hopefully know that the only difference between the cosine and the sine function, if you're looking at a graph, is one is shifted with respect to the other. And so and you can always shift a function just by an additive constant. So which one we choose is really quite arbitrary. You'll find some textbooks that pick out sine. The textbook we're using in our class picks out cosine, so we'll go with that. But it doesn't really matter. These are both cyclical functions, so they both can be used to describe this motion. You'll find out in later courses there are other ways to describe this motion with other cyclical functions. There are different ways to express sine and cosine in terms of the exponential function that you can use. For this class, we're going to stick to cosine, but any cyclical function will work just fine. So here's what we need. We need whatever mathematical formula we come up with to give us some values in these particular places that are reasonable. So I think probably what we'll start out with is, oh goodness, trying to come up with an equation for the position of this thing as a function of time. And the as a function of time part is going to be important there. We're characterizing these things with time because we understand that the oscillations are happening cyclically. That means every period later, I'm in the same position that I was before. So we're going to characterize these things as functions of time. Okay, so we know that x of t is going to be some sort of cosine function. So I'm basically just going to give you the punchline here. We're going to characterize this as omega t. Remember, omega is my angular frequency. It's got units of 1/seconds multiplied by time, which has units of seconds, cancels my dimensions, which is what I need because the argument of a trigonometric function must be dimensionless. So I've got 1/seconds times a second, I should say, gives me the right units. Your book, if you're in my class, starts this out a little bit differently. I'm not going to go into it a whole lot, but I will show it to you. Your book starts this, I'm actually going to do it on a different sheet because I don't want to destroy my train of thought, is x of t is equal to this cosine 2 pi over t, the period, times t. From that, you get that this is 2 pi times 1/t. I just separated them out. That's equal to 2 pi times f, the frequency, right? 1/the period is the frequency. And then that's equal to omega. That's just how we define omega, as 2 pi f. The 2 pi becomes important because that is the angular period of the cosine function. And so if we're trying to have this thing repeat every period, the 2 pi is going to come in there. And then the units here cancel to give you a dimensionless function. Basically what this says is that when t is equal to the period, right, you get a cosine of 2 pi. So this repeats cyclically. We can control when it repeats by, well, we don't control it, but we describe how long it takes to repeat with the period here in the denominator. And then this time is our stopwatch time, right? It's what's running. And this enables us to find out when the cyclical motion repeats. So when t is equal to some integer multiple of the period, right, I get cosine of something like 2 pi. Right, when t is equal to t, I get cosine 2 pi. When t is equal to 2t, right, I get cosine of 4 pi. When t is equal to 3t, I get cosine of 6 pi, and so on and so forth. Of course, these are the same values, so there's the cyclical nature. So this is where the equation that we're developing kind of has its genesis. You don't have to start it this way. Your book doesn't actually like it. I said I wasn't going to get into it, then I got into it. But that's okay. I like this, although I'll probably never write it again. This maybe gives you a little bit more intuition about where this equation comes from. So at least that is part of it. Now, what we need to take into account is that this position is going to have something to do with the amplitude, right? So if we get t is equal to 0, and I'm assuming that t is equal to 0 here. I'm starting my stopwatch when I'm letting this thing go. Then we're going to say that t is equal to 0. I'm going to get a cosine of 0, which is a 1. I need to take into account the amplitude of this thing. I've actually started it at the wrong side, haven't I? Shoot. Okay. Fair enough. Let's run this backwards. And if this does go backwards, right? It goes this way and this way and this way and this way. So just for the purposes of rescuing my own derivation here, let's start it here where a is positive. So we're going to let t is equal to 0 be here. Then it's going to come this way, go over here and have an amplitude of negative a, or a displacement of negative a, come back, have an amplitude of, or a displacement of a, come back, displacement of negative a, so on and so forth. But we're going to start this over here. Again, you don't have to. You're going to get a slightly different equation, but let's start our stopwatch over here. So t is equal to 0 here. Now, if t is equal to 0, cosine omega t gives me cosine of 0, which is 1, right? Well, what is my position at this point? My position is a. And so to complete this, or almost completed, I need to put a multiplicative constant of a here. This is the amplitude of the motion, right? So when I'm at this position, the cosine omega t gets me 1, and I get the displacement. The position as a function of time is at a. As I move back, right, I get the cosine omega t here is going to get me a 0, and I'm halfway through, actually I'm a quarter of the way through the cycle, right? I start here, this is a quarter of the way through, this is half of the way through, this is 3/4 of the way through, this is all the way through. So a quarter of the way through the cycle gives me a cosine of not 0, but cosine of 90 degrees, which is going to be 0. And that gives me a displacement of 0. So this is matching up really, really well. As I get over here, I'm halfway through the cycle, and if you think about something, moving around the unit circle, I start the cycle here. This is a quarter of the way through the cycle. This is halfway through the cycle. I get a cosine of 180. What is the cosine of 180? It's -1. And I get that the displacement is a times -1, -8. This is why I needed to start it over here so I wouldn't mix up my negative signs. And so on and so forth. I get back here. And so this equation seems like it does a really, really good job of describing this motion. So I think this is what I'm going to go with, right? This is this is almost the position equation as a function of time. Now, once you have this, or if you're given this, it's actually really lovely. You can just read information off of this. Like, let me give you an example. If you showed me this and you said, this describes some cyclical motion, some oscillation, what's the amplitude of the motion? I can just read the information off of it. 1.5 meters. What is the angular frequency? 35 hertz. What is the linear frequency? 35 divided by 2 pi, because that's the relationship between F and omega. Right, so once you have this equation, you can actually just read off information from it. It's quite lovely. The discussion of this takes a bit of time, but the actual mathematics involved is really not terrible. You can very often just read this off. Okay, so this is almost complete. What I have to take into account is that I don't have to start my stopwatch here, right? I could have started my stopwatch over here. I could start my stopwatch here. I can start my stopwatch when it's halfway between these two positions, right? How can I handle that? Well, mathematically what's going on is I'm shifting my function, right? Notice if I start my stopwatch at this position, I need to get a 0 for the displacement. So the time is equal to 0 because I started here, but this function does not give me a 0 here, it gives me a 1 now, because I'd have a cosine of 0. It gives me a 1. And so this equation turns out to be really, really good as long as I'm starting my motion over here. But that is clearly not good enough for our purposes. We need to be able to start our stopwatch anywhere in this motion and have this equation get us what we need. The solution for that is to add what we call a phase angle, a cosine omega t. And then I'm going to add to that plus phi, where phi is what's called my phase angle. This is basically some insurance to say that you can always make this equation match your physical conditions no matter where you start by adding a constant to the argument of your function, basically.